What's up, folks? This is Ref Bari, Brown University physics grad student. Today, I'm very excited to bring you the next lecture in advanced statistical mechanics. Now, today's lecture is going to be very exciting. We're going to be talking about phase transitions, one of the most catastrophic things that happen in physics, but that happen every day in your refrigerator or in your kitchen. See, when you put a pot of water on your stove, that water turns from liquid to gas. When you put a little bit of water in your freezer, that water turns from liquid to solid. So these phase transitions form the building blocks of our everyday life. If there were no phase transitions, then the ground would be connected to the sky. The sky would be the same phase as the ground, right? There would be no solid, gas, or liquid distinction, and everything would be a kind of soup. Everything would be the same phase. So it's really critical to understand the theory of phase transitions and phase transformations, because it forms the bedrock of not only fundamental physics but our everyday world, right? So let's get started with the phase diagram of a normal object, maybe not water but an arbitrary object. So here is a phase diagram, and in this phase diagram I'm going to have two phases. Maybe they're solid and liquid or liquid and gas. Take a look. This is density on the x-axis, temperature on the y-axis. Here I have a liquid phase. Here I have a gas phase. Here I have a two-phase coexistence of the liquid and gas phases. And that's it. Okay, so that is it. And here I have one phase. Let's say that this maximum density is rho plus. This minimum density here is rho minus. And the central density here, I'll call it rho C. And the maximum temperature here, Tc. So rho C for critical density, Tc for critical temperature. So I've got a basic phase diagram here. Now, what's interesting about this phase diagram is that, first of all, you have two phases here. You have a liquid phase and you have a gas phase. Okay, so what's the big deal here? Well, the big deal here is that you can go from liquid to gas in one of two different ways. The first way you can go is directly start from liquid and then just at the same temperature, just lower the density of whatever fluid you're considering. And so then you'll start from the liquid phase, transition into the two-phase system, and then go into the gas phase, okay? So this could be, for example, if you're putting a pot of water on the stove, right? Here's your stove, here's the pot of water. Then that water is going to start as a liquid, right? It's in the liquid phase originally. But once you increase the temperature, here of course we're keeping the temperature constant but lowering the density. But in this analogous case, when you increase the temperature, then we're going to have bubbles of water vapor form and the liquid is going to transition into a gas. But in between the liquid and gas, there is a small interface where we have both of the phases, liquid and gas, okay? And that's that two-phase system right here in the middle. But we don't necessarily have to undergo a phase transition to go from a liquid to gas. Because check it out, if I just increase the temperature first and then lower the density and then decrease the temperature again, well then I've gone straight from a liquid to gas, but without trespassing the phase transition boundary. So in other words, I can go from a liquid phase to the gas phase of a system without undergoing a phase transition. So that tells you that maybe the liquid and gas phases of matter are not all that different. And in fact, it'll turn out later in statistical mechanics that liquid and gas both have the same kind of symmetry. So liquid and gas both have the same symmetry, but liquid and solid do not have the same symmetry. In fact, the liquid version of water has a higher degree of symmetry than solid, ice water, which is why you cannot transition from liquid to solid without crossing the phase transition boundary. And we'll see that shortly. But this is a classic example of how counterintuitive phase transformations can be, right? Just because you're going from liquid to solid, two qualitatively different phases, does not necessarily mean you have to trespass the phase transition boundary. Now, this whole picture right here is, we can mathematically categorize this as follows. Okay, so 0.327. So physicists have taken this phase diagram and they've written down a kind of equation which describes the relationship between our density and temperature variables here. So they've written down that the difference between the max and minimum densities is somehow proportional to the temperature minus the critical temperature to some exponent, 0.327. Now this exponent right here is called the critical exponent, okay? That number is not special in any way, shape, or form, but what I'm trying to say is that different observable quantities, different thermodynamic quantities in thermodynamics, for example, heat capacity, pressure, density, temperature, electric field, magnetic field, these different observable quantities, they're dependent on power laws, okay? They're dependent on power laws. So for example, here's another famous example. We have pressure, temperature, and we have something that looks like this, where we have gas and a solid. This is not something that you have to remember, of course, so I'm just copying it down. This is a normal fluid. This is a superfluid. And here is where you see that phase discontinuity. Okay, great. So this is the phase diagram of liquid helium, or helium-4. And here you can see another property of phase transitions, which is they usually involve a discontinuity in an observable parameter. So for example, in this graph, we have heat capacity C versus temperature T. But at that critical temperature T lambda, where liquid helium undergoes a phase transition, you can see at that phase transition, our heat capacity diverges. Our heat capacity diverges right here. And so this is another critical element of phase transformations. When a physical system approaches a phase transition point, then you'll have a critical parameter, a critical observable like heat capacity or density or pressure. These will approach some kind of a diverging quantity, okay? That's the idea. And another important fact is that these critical exponents denote how quickly the system approaches the phase transition point. It denotes how quickly the system diverges at the critical temperature, which is, for example, here T lambda, here it's Tc. So now that we have a kind of heuristic idea of what constitutes a phase transformation, let's go a bit deeper. To get another idea of phase transformations, let's take a look at magnetization of a system versus temperature. And what is magnetization? Magnetization is basically the spin alignment of a bunch of atoms. So for example, if I have a bunch of atoms that are pointing up or down, okay, spin up, spin up, spin up, spin down, down, up, down, whatnot, right? All of these atoms, they have a net magnetic moment, right? If you add up all of their spins. And so the average magnetization, M, is defined something like 1 over n times the spin of each one of these atoms, okay? So how does the average magnetization of a system change depending on temperature? Well, that is actually very interesting. First, there's a critical temperature T sub C above which there is no magnetization in a system. And that kind of makes sense, right? If your temperature is too high, then thermal fluctuations will ensure that there's really no preferred spin direction. So every atom will be in a random spin orientation, either spin up or spin down. And on the net whole, the total spin, the total magnetization, has no preference but to be 0, right? There should be no preferred direction, spin up or spin down, if the temperature is too high, because thermal fluctuations will kill any kind of preferred orientation. But below that critical temperature T sub C, the net magnetization looks something like this. Okay, and this is a very interesting shape. What does it show? Well, first of all, let's deploy some terminology here. The paramagnetic phase of our spin system. And in that paramagnetic phase, we have no preferred spin direction, right? Thermal fluctuations kill any spin direction. Below the paramagnetic phase, we have the ferromagnetic phase. And in the ferromagnetic phase, there is a preferred spin direction, okay? So for example, all of the atoms or some of the atoms might want to point up while others point down, but nevertheless, there will be a net magnetic moment where more of the atoms are pointing up than down, or vice versa. And so that is the ferromagnetic case right here. And this kind of a phase transition, where we go smoothly, continuously from one phase, ferro, to another, paramagnetic, when we have that kind of a continuous phase transformation, well, this is called a continuous phase transition. Phase transition is some kind of an observable that varies smoothly between phase transitions. Okay, and we have one more thing to say. When we are in the ferromagnetic phase, then there is a net magnetic moment in the system. Net magnetic moment. Alrighty, net magnetic moment. So that helps us kind of get to grips with this basic kind of thermodynamic phase transition. You have the ferromagnetic phase below the critical temperature. This right here is the critical temperature at which the phase transition occurs. Critical temperature. And above the critical temperature, you have the paramagnetic phase, where there's no preferred spin. And whenever you have an observable quantity, for example, magnetization or some other property of the system that varies continuously between the phase transition, then that's called an order parameter. And this is a continuous phase transition. So, okay, now let's dive deeper into the math. Okay, so in thermodynamics, the key idea is to obtain two things. First of all, the partition function z. This tells you, first of all, what is z for the unacquainted. Z is called the partition function. It is essentially a normalization factor in thermodynamics, but it's really much more than that. It encapsulates everything you need to know about a system. If you want to know the temperature, the energy, the entropy, the pressure, anything you want to know about the system is contained by taking different derivatives of the partition function. Okay, now that's one thing, the partition function. But another thing in statistical mechanics is the free energy, F. See, the free energy is a function of all these different observables, for example, pressure, energy, number of particles, volume, entropy, so on and so forth. So the free energy is really the entire package. All the thermodynamic quantities you want is contained in the free energy or its derivatives. Okay, so what a phase transition really is it's when the free energy hits a discontinuity. Okay, so let me phrase that another way. The free energy depends on all of these variables. I'm going to call them x sub I. Okay, so the free energy is dependent on these observable parameters. And when the free energy has a discontinuity, okay, in other words, when partial f partial x sub I does not exist at the phase transition point, then we have a phase transformation. Okay, so one example of that could be, for instance, when we had the heat capacity against the temperature, I believe, and we had something like this for liquid helium, where this was the critical temperature, T sub lambda. And so at that point, you can see that the heat capacity diverged at the critical temperature. And another way to phrase that is, if we found the free energy at that point, okay, at T sub lambda, then this would be, it does not exist, right? Because we have a discontinuity here, clearly, right? It diverges. So an even stronger statement to make would be to say that what kind of a discontinuity do you have? What order phase transition do you have? So this is a kind of classification that was first discussed by Paul Ehrenfest, who had an unhappy ending in life, unfortunately. But Paul Ehrenfest came up with a scheme to classify different types of phase transformations. Paul Ehrenfest said that if, for example, you have a first order phase transition, then partial f partial x sub I at the phase transition point does not exist. It is not defined. But you could also have a second order phase transition or nth order phase transition point, where the nth derivative of the free energy with respect to that observable at our phase transition point does not exist. Okay, so that's the idea. That's the big idea of first and second order phase transitions. This right here, for example, would be an nth order phase transformation. Phase transformation. But this definition, the Ehrenfest classification of phase transformations, doesn't really hold up when it comes to, for example, the heat capacity diverging at the critical temperature. Why? Because we don't really have a discontinuity here. A discontinuity would look something like a hole in the graph for the heat capacity. We don't have a hole. No, it's more like the heat capacity completely diverges at the critical temperature. So the Ehrenfest classification of phase transitions is not really a descriptive or honest way of describing phase transformations. Instead of saying that there's a discontinuity, we should really be saying that there's a divergence at the critical temperature. There's a divergence of the observable quantity, for example, heat capacity, at the critical temperature. So let's really mathematically quantify the idea of phase transitions. Let's try to do that. Let's start with the free energy of a system. I'll call that F of sigma, okay? F for free energy. Now, we know that the free energy of any thermodynamic system is an extensive quantity, meaning if you double the size of the system, the volume of the system, the free energy too shall double. So we expect the free energy to be in some way proportional to the volume of our system. And in fact, we can mathematically write this down as follows. The free energy of our system should be equal to the volume of our system, V of sigma, times the density of the bulk free energy, F sub B. What is the bulk free energy? Well, consider some kind of a thermodynamic system. Okay, here's a box. Maybe there's a gas in the box, maybe there's liquid, maybe there's solid, whatnot. Now this box has some kind of a volume, V of sigma, but also it has a surface area. It also has a surface area given by the walls of the box. And I'll call that surface area S of sigma. So we should expect there to be a bulk free energy within the box. That bulk free energy, F sub B, will dictate the changes, the thermodynamic changes, the phase transitions inside of the box. But there's also a free energy associated with the surface of the box, the free energy on the surface, F sub S. So now we have not one term, the volume times the density of the bulk free energy, but also the second term where you have the surface of the thermodynamic system times the density of the surface free energy, F sub S. Okay, now notice something. First of all, the volume, V of sigma, this is D in dimensions, D order in dimensions. What does that mean? That means that if our thermodynamic system has some characteristic length L, then, well, of course, the volume of the system will be proportional to L to the D, where D is the dimensionality of our system. For example, if you have a sphere, then the volume of the sphere is simply proportional to R cubed, and the surface area of the sphere is proportional to R squared. So this first term, V of sigma, is proportional to L to the D, whereas the second term, S of sigma, is proportional to L to the D minus 1, and we might have a third term correction. So I'll call that O of L D minus 2. Anything beyond third order corrections is just not worth writing down, right? So this is what we have right here. So now if I want to solve for the free energy, for the bulk free energy density, F sub B, so if I want to solve for the density of the bulk free energy, the first thing I have to do is take the thermodynamic limit of my system. The thermodynamic limit of my system as the volume of my system approaches infinity. Because you see, only in that case, only in the case where my system becomes infinitely large, does the mathematical theory of phase transitions work. This is indeed a serious deficiency because there might be finite order, finite size effects for systems having phase transitions. And of course, we know that nothing in reality is infinitely big. But this is what makes the math work. So this is what we're going to do for now. We're going to take the thermodynamic limit. This right here is the thermodynamic limit. Thermodynamic limit. And after we take the thermodynamic limit, we're going to put in our, let's see, so we have the limit as v approaches infinity. We're going to take the total free energy of our system and divide it by the volume of our system. So this right here is the definition of the bulk free energy density. Bulk free energy density. It's simply the total free energy of our system divided by the volume of our system as the volume approaches infinity. And now likewise, we can do the same thing. So this is the free energy per unit volume, but we can also say that the free energy per unit lattice site is the limit as the number of lattice sites approaches infinity of the total free energy F of lambda divided by n of lambda. Okay, so this is the free energy per lattice site if we're dealing with a lattice system. Free energy per lattice site. Okay, very good. So now what does this mean? That means that, first of all, if you are expanding a thermodynamic system out to infinity, then you have to take both the volume of the system, V of lambda, to infinity, and the number of particles or lattice sites in the system to infinity, so that the number density, N of lambda over V of lambda, stays constant. Okay? Otherwise, it would be senseless. What are you taking to infinity if you don't keep the number density of particles or objects in the system constant? So given this, we have this definition for the free energy per lattice site of our thermodynamic system, and this for the free energy density of the bulk system. Okay, now what about the free energy on the surface, the free energy density on the surface, rho F sub s? Well, that's actually very easy to solve for, right? Let's go ahead and solve for that. We're just going to make the approximation that this second order term is negligible. So in that case, we have what? The bulk, sorry, not the bulk, but the free energy density on the surface is simply given by the limit, once again, the thermodynamic limit that the volume of our system approaches infinity. And then we have F of lambda, the total free energy, minus the volume of our system times the density of the bulk free energy divided by the surface of our system. Okay, so this right here is, this right here is how we calculate the surface free energy. Okay, this is the surface free energy density. Free energy density. Okay, so this at least gives us a start for mathematically calculating the free energy of a thermodynamic system and noticing when there might be irregularities, discontinuities, or divergences in the free energy. For example, as in the case of when we had the heat capacity versus temperature for liquid helium, then you could very clearly see this phase transition at the critical temperature right here. So now that we have some mathematical formalism, let's dive deeper into the idea of phase transformation. Now what we're going to show is that certain forces, for example, electricity and gravity, are too long range to have thermodynamic phase transitions. Now, this is a basic thermodynamic theory in statistical mechanics. It doesn't account for example, Hawking's laws of thermodynamics and black holes, but it gives us a sense of idea why gravity or electromagnetism might not have any obvious thermodynamic properties. Okay, so where do we get started with that? Well, let's consider a charged spherical ball. Okay, so let's say we have a ball of uniform density rho, of volume v, and a total radius capital R. Okay, what is the energy needed to construct this ball? Well, we can simply write the potential energy of this ball is Q times V. So an infinitesimal amount, du, is simply V times dQ. Okay, now what is V? That's the electrostatic potential. We all know what that is. That's simply KQ over R times dQ. Now what is Q? Well, Q is the existing charge in our ball. Okay, so let's say that this is Q. Okay, let's say our ball, our charged spherical ball, currently has a radius of lowercase r, and we're adding on charges to our ball. Okay, until our ball eventually reaches a radius of capital R. And the thickness of our ball here is dr. So what does that mean? That means we have, first of all, what is Q? Q, the total amount of charge here, is simply the volume of the ball, 4/3 pi r cubed, times, I guess that's it. Yeah, that's it, times the density, the charge density. So that's Q. And what is dq? Well, dq, well, simply take the derivative here. If I take the derivative, dq is, let's see, 4 pi r squared rho. Okay, so then what do we have for our total electrostatic potential, or our total electrostatic energy? We have U. If I go ahead and integrate this, then I get U is the integral from 0 to capital R, where capital R is the total radius of our sphere, kq over r. Now k, I'll just leave it as k over r. Now q, I'll replace with 4/3 pi r cubed times the density of my charged spherical ball, and dq is 4 pi r squared rho. All right, that's great. Now I have everything I need. Remember, this is dr. Let's go ahead and integrate this out. So I've got, first of all, r takes out one of these r's, okay? And I'm integrating with respect to r, so I can pull out all the constants here. So I've got 4/3 pi squared. I've got another factor of 4 rho squared. I've got k. So I've taken out all of these, okay? Rho squared, k. And I've got the integral of r to the 4, which is simply going to be r to the 5th over 5, okay? And let's just simplify this a bit. So this is going to be 16 over 3, or 16 over 5, 16 over 15, 3 times 5, pi rho squared times k times r to the 5. So this is the total energy of our system. Now, if we take a look at the ratio of the energy of our system, E of r, to the volume of our system, V of r, we'll see that this quantity diverges, okay? This approaches infinity as the radius of our spherical ball approaches infinity. So in other words, as your charge distribution gets bigger, the energy per unit volume required to create that charge distribution also approaches infinity. So this right here, this divergence in something as basic as the energy per unit volume required to create this spherical charged ball shows that electrostatics is simply far too long ranged to have phase transitions because it simply diverges, right? So another way to see that is that when you have 1 over r potentials, for example, as in the case for Coulomb's law or Newton's law, universal law of gravitation, both of those are 1 over r potential forces, 1 over r squared in the actual range of the forces. Those forces are too long range to permit phase transformations or other thermodynamic properties.